Great to be here. I've attended a couple of these events. I find them very valuable, so I'm really quite honored to speak at it. So I'll start with the name, which is probably going to be the most exciting part of the presentation, I'm afraid. So, we wanted to be evocative of the database's capabilities, and this is primarily about survivability. This database is supposed to be resilient to large-scale failures. And also, we wanted to capture some sense of autonomy, like each one of the nodes in the distributed systems is pretty anonymous and will kind of colonize the available data storage space, just like cockroaches in your kitchen. So we started this as an open source project last February, me and a couple other people, and we worked on it over the course of a year. And luckily, we were bored with our jobs enough to decide to actually start a company around it, and we raised money recently from Benchmark and Google and Sequoia and FirstMark. So we have some really good investors on board. And as Matt mentioned before, we have some really great engineers already who have a lot of experience in related projects, which I think is going to inform both the design and implementation of this one. So this is a fanciful timeline of databases. And it kind of, it mirrors my career, and I think it gives a little bit of background about why we're building Cockroach. So the granddaddies of databases, starting really in the 1970s and really peaking in about the year 2000, were the traditional RDBMS systems, Oracle being really the 800-pound gorilla there these days. But they were standardized with SQL, structured query language, on top of them, and that gave them wide adoptions. And over the years, it became really great for building applications. But they started showing signs of age around the dot-com days, when companies went from sort of enterprise level to really having to wrestle with this problem of web scale, of having a large fraction of the people online possibly being customers. So RDBMSs have pretty poor horizontal scalability. You can put money into the problem, but that has limits. Ultimately, what people do is they shard the databases. And I ran into this really head first, into a brick wall when I got to Google in 2002, and they were using sharded MySQL in order to run their AdWords backend. And they went from 8 shards to 12 shards to 30 shards. By the time they replaced that system, they'd gotten up to 1,000 shards of MySQL. And you can imagine that's actually quite a bit of operational headache. So, around the 2000 and to 2004, when Google published a paper about a system called Bigtable, is sort of a parallel track to sharding RDBMS databases. And this was the advent of NoSQL, and we're all quite familiar with that. And it's still with us today, and it's quite popular. So NoSQL, the idea is let's trade some of the cool capabilities that evolved with RDBMS systems for a simplification that allows to solve the horizontal scalability problem. So these were scalable and available. The problem was that there's no SQL, no query language, which means that applications have to do manual joins. And also, some of the simplification lost concurrency control, so transactions. And that actually turns out to be a very, very useful thing for building applications, meaning that most NoSQL systems, it's kind of an uphill battle against them. It's great for the scalability, but it's an uphill battle to build complex applications on top of them. And it's interesting because NoSQL is very widely embraced in the industry today. But by 2006, Google had moved away from it for building applications. By 2006, they published a paper called Megastore. And this system was something that 150 to 200, I think, applications that are externally facing at Google were ported over to. Developers essentially voted with their feet and overrode the infrastructure group and built Megastore, which was built on top of Bigtable, to give it transactions and to give it consistency across wide areas so that every application could have a disaster recovery story. So Google kind of took this to heart, and the infrastructure group reimagined Bigtable and to something called Spanner. And that paper was published in 2012. Spanner is really the advent, and Google does this a lot with databases. They're constantly evolving, but of sort of the next evolution of databases. And some people call it NoSQL++ or NewSQL or SumSQL. The idea is that the baby got thrown out with the bathwater, and then maybe that shouldn't have happened. And we want the cake and eat it too. So you have scalability, of course, transparently, but you also have consistency across wide areas, and you have transactionality and other things actually that make building applications easier. So the problem as we see it, and I think it's important to kind of look at this from how important databases are. They're kind of easy to lose track of with all the other crazy things that are going on with machine learning and data science. Databases are really the beating heart of every business. And when I'm talking about Cockroach, it's important to think about OLTP databases. And also, there's a constant evolution that's been going on for the better part of 45 years now. And it's really an evolution between the business requirements versus the capabilities of the databases. And the databases are always lagging. And it's really an arms race between those two. Today, I think startups have three real options. And the problem is that if a startup succeeds, and especially if the startup succeeds wildly, none of these three options is very scalable. So the RDBMS, they don't scale horizontally. So you're going to end up sharding if you're really successful, which is not a good option. NoSQL. The problem is that, in this day and age, mobile apps are getting increasingly complex. And when you have a complex mobile app, that translates to complex operations that are run in the cloud on the back-end servers. And the problem is that these NoSQL systems just aren't sophisticated enough to handle those. Hosted services like DynamoDB, Amazon's Aurora, Google's cloud storage, the problem with these is you've got vendor lock-in, and they're all proprietary. So when you actually do want to switch off it because you've become Dropbox or the next Dropbox, that's an incredibly expensive proposition. So our idea, and I think from like a really high level, the important thing for us is this is like scratching an itch that we've had. We've had it since we left Google. We had it at Google. We've had it at the companies that we've started and the companies that we want to start next. This is what we want to build. And we also think it should be open source. Open source gives customers a huge amount of optionality. You have, of course, you get to avoid the vendor lock-in. You also have, I think, a better support concept, which is much better community support. And you also have the flexibility to debug all the way through the stack, right into your database, and as well as to customize it if necessary, which a lot of companies actually do end up doing. So we want to address the challenges for really an increasingly global and increasingly mobile set of companies, and we see this over a 10-year time frame at least. And this is not the entire set of them, but really a scale, survival, consistency, and this involves even consistency across wide geographic areas. Companies are becoming more international, and also complexity. So if we had to boil down the goal into a nice terse little catchphrase, it's make data easy, because data is not easy right now. It's incredibly difficult. And if you take all the money that's spent wrestling with database shortcomings and you use that time and money and engineering resource in order to make your company stronger and your product better, everyone's going to be better off. So how do you make data easy? Well, you want to avoid success disasters. So you want to be able to start small, but you also want to be able to grow to a Fortune 500 company. And you want to do that without having to change your whole database infrastructure. It's a very expensive cost. You want to do it with horizontal scalability. So that means that you can add commodity hardware in and get a proportional amount of capacity out on the other side. And however you do it, you want your apps to be agnostic. They should not have to understand it. That adds a lot of complexity and it makes it difficult to iterate. So you also want to survive the failure disasters. We're aiming to actually handle incredible failure disasters like an entire data center going away. And the idea here is that when the data center goes away that your application's running in, your apps don't care. Leave that to the AWS people, leave that to Google's cloud people. You shouldn't have to notice. If you can do that, you should also be, of course, able to survive very simple things like OS upgrades, server or container or virtual machine restarts, as well as disk failures and machine failures. And you want to do this with no operational overhead. So it has to be automated. Automated rebalancing in the case of adding new resources into the cluster to grow it, and also automated re-replication in the case of things failing and you need to re-replicate to other sources. So increasingly, you want to move your data over a wide area. And this is actually a big problem for most database systems. Most database systems do something called eventual consistency. And what that means is there's a lag between having your data where it's originally written and to where it may be backed up for disaster recovery in case you have to have a failover. There's an alternative, which is called strong consistency, and this is what Cockroach is going for. It's what Google's built into Spanner and actually had in Megastore as well. There is a cost to strong consistency. You have to get consensus between essentially a majority of data centers that are participating. But the nice thing about strong consistency is it makes your applications very straightforward, very simple, and very easy to reason about, so you're more likely to be correct. It's actually an incredibly hard problem. It's incredibly hard to solve it above the database layer, which some people purport to do. They're putting all these kind of checks in. Oh, well, was I at this data center before? Am I at this data center now? That doesn't work. It actually is incredibly hard to do at the database level as well, and there's a lot of databases out there that make claims to do this, and they consistently fail to do it. So I'd be very suspicious if you see a database that claims to do this that doesn't use something like Paxos, which is really the gold standard, and Raft, which just came out in 2014, which is kind of a reimagined and simpler version of Paxos. Finally, what we're really trying to do is allow developers to build apps and not constantly be building workarounds. And here's just 3 things that I think matter. Transactions, I think, matter most. Transactions are these ACID semantics that you probably learned about in a computer science class back in college. And it's all or nothing. So, wherever you happen to be in an operation and a failure occurs, anything that that you've done up to that point just disappears, and nobody could have seen it in an intermediate state. It's very important. It simplifies the code, cleans up the possibility of these incredible data messes when you have a real bug in your system. Also, indexes. These just are what every application needs, and crazily, NoSQL systems, most of them don't provide them by default, and people have to build them into their applications. It takes a lot of time, and they're often not correct. And also flexible schemas. If you're going to have a schema, you should be able to add columns to it without any kind of downtime or any kind of lag, and you should be able to make changes to the schemas without locking up your database. So I'm going to do a very quick dive into the architecture so that there's a little bit more meat into this talk, and it's not just the high-level concepts. So we implement a layered architecture, and this is important because we're trying to manage complexity. It's an open source project, so we want everyone to be able to participate, and some people are more comfortable at other layers, some layers and some in other layers. And so, this allows the upper layers to treat the lower layers as sort of functional black boxes, and the lower layers don't even have to be aware that the upper layers exist. So these top 2 layers are logical. The very top, SQL, is aspirational. We do intend to do it, but we haven't started working on it yet. Beneath that is the structured layer, which we're currently working on. Structured it has these standard RDBMS concepts like schemas, tables, and indexes. And that's, as I said, under development. So the structured layer actually talks to this foundational, it's the last logical layer, and we call it here the distributed key value store. Essentially every database, whether it's a graph database or a relational database, is built at a lower level on top of a key value store. We implement ours as a monolithic sorted map. For those of you that are interested in databases, this is in contrast to another very popular architecture, which is called consistent hashing. It's something that Cassandra uses, for example, and React and several others. A monolithic sorted map is something that makes it very easy to do very large global indexes. This is what Bigtable used, HBase uses, and also some of Google's newer architectures like Megastore and Spanner. So the distributed key value store is actually what's responsible for taking requests from the structured layer and translating those into RPCs that go out into the distributed set of nodes. So we have this in this list, and it's a kind of funny thing in the architecture section, but it's important. These distributed transactions, this is a fundamental part of the system. You see a lot of the sort of distributed databases that currently exist attempting to sort of retrofit their database with distributed transactions. It's very difficult to do that post hoc. You can see here that on the right side, there's all 4 of these bottom layers are highlighted because the distributed transactions really suffuse through all of them. So these bottom 3 are the physical parts of the architecture. So nodes correspond to physical devices or physical machines or virtual machines or containers. Each node has some number of stores. Stores correspond to virtual devices or physical devices. Every store is managed with RocksDB. RocksDB is another open source product. It's from Facebook. It's written in C++. It's based on something from Google called LevelDB, which is really at the heart of Bigtable. And finally, every store has a number of ranges. Ranges are the sort of smallest part of our key space. They together make up the entire monolithic sorted map. The range is where we do our replication. So we use Raft, which is a variant of Paxos, to consistently do that replication. So in addition, we want to have a very simple deployment. And this is important in this day and age when people are reimagining all of their architectures for this world of containers. And we think this is an important trend and one that is actually incredibly beneficial to us in terms of adoption, because the way that we've designed Cockroach fits with that model very well. Many of these systems are very heterogeneous in their deployments. There's masters and slaves and secondaries and primaries, and there's global configuration. And in order to put all that out into a containerized world where you really want these anonymous, very symmetric kinds of containers is difficult. It's hard to keep track of, and you have a lot of single points of failure. With Cockroach, nodes are symmetric. There's no single point of failure. They can all take on the same roles and responsibilities. And there's no external dependencies. We don't have Zookeeper that's holding global configuration. There's a single binary that you just put into a container, and you just put as many as you want out there in multiple availability zones, and kind of think of a bunch of little cockroaches colonizing and coordinating amongst themselves. So this thing self-organizes. That's how it avoids having this global configuration. It does that with a gossip network, which is really a peer-to-peer network where they communicate. So a new node will join that, communicate with the others, and discover that it has more capacity, than the mean of its neighbors. And so it'll start to auto-balance and share its information. And of course, when something goes away, the same thing happens. The other ones that had been replicating to it, replicating their ranges to it, notice that it's gone, and will identify another node and re-replicate. So to meet this goal, to make data easy, I was actually writing some of these things up here and realized that, this again is very much like the insect. So the name seems like really the perfect name, even better than I thought it would be at the beginning. It's born to scale. Those things really do manage to scale. You see one of them, you're going to see 10 of them next week and 100 the next week. We all know this. We live in New York. I have a personal history with cockroaches. I hate them more than you can believe. So they're also auto-balancing, self-repairing. Cockroaches can, live through having their heads cut off for like 30 minutes or something horrible like that. And they're one of nature's most successful designs evolutionarily because they're simple. I think they've been around for 300 million years. And finally, the whole goal of this is to stop saying maybe. This is really a dangerous word when you're talking about a mission-critical data storage system. And these are questions you should ask attached to each one of these points. Do you have a single point of failure? What happens if a node goes down? What happens if a data center goes down? And as far as consistency goes, I think the key point here is when you write something and then you go to read it, will you always read what you just wrote? That's the big question to ask. And if you're asking that question, think about what will happen to your application, what will happen to your data if that's not true. And I'd say that the use cases range from it doesn't really matter because it's the number of lights that are showing up on a page to this is disastrous, it's an absolute no-go. But it's important to ask that question. And finally, transactionality, is if the operation that's running fails at the worst possible time, what will happen to your data? Thank you.
Very nicely done. By the way, I love the design of the cockroach. That has to be the best-looking cockroach I've ever seen. So where are you in the process of building all of this and launching and, for anybody that wants to become an open source community contributor?
So it's still in the alpha stage right now. So I wouldn't recommend anyone put it into production. We've had a tremendous amount of interest from especially three-letter government agencies. And also from some big international companies, in particular in China. I think they're seeing a lot of use cases where just off the bat you're going to have hundreds of millions of people that you have to deal with. And also find in the international arena, even new companies are looking at their potential customers in a very global sense. Everything just has to start international because they're not starting with such a huge built-in market like companies in the U.S. So they're coming in with problems like, well, we have to have data centers all over Europe, and they all have to be fast for local reads, or they have to even be from Brazil to China and to Mexico. And so those kinds of use cases are ideally suited for Cockroach. So interestingly, we've gotten a lot of help from those companies too. We actually have open source contributors, like a whole team of 10 people from China, for example, and some people from the U.S. government, because they're so interested in it. So we're hoping to get the beta out by the end of the year.
It's kind of amazing that the U.S. government would be an open source contributor.
They're very new to it and very scared of it, but they're trying.
Is it, and I have a sense of, I mean, obviously what your answer is going to be, but is it possible to build a good technology company these days, not in an open source manner? I mean, to build proprietary software?
I definitely think so. I think that, as far as databases go, you can have a lot of luck with a proprietary solution if you are building something that's very niche, that's never been seen before. What Cockroach is doing is an evolution of databases that are very good that already exist. I think that it would be a mistake for us or for anyone like us to build something that's closed source in terms of a general OLTP database system.
Great. One question over there.
So you basically said that there were some disadvantages to startups, like in their choices for databases. And I was wondering, since you mentioned, and it makes sense to me, why the Chinese population and US government would be interested in Cockroach. What startups would be interested in Cockroach compared to, say, hosted solutions where you don't have to manage it yourself?
So I actually think that hosted solutions are a great way to build a startup. It's quite possible that we'll offer it as a hosted solution. I'd say that the biggest disadvantage to a hosted solution is, if you do build the next Dropbox, or you do build the next, God forbid, Facebook, then, you have this problem with the success disaster, where with a hosted system, you get that vendor lock-in. And Dropbox has been struggling with this. They built their whole own alternative to S3, but they still haven't been able to move off because pulling their data out of S3 is like sucking water out of a swimming pool with a straw. And it's easier to move all the disk drives out, but of course they can't do that. So it's very hard to move out of there. And that's not the only problem, of course. The idea with open source, with this solution, is that even if you were using it in a hosted fashion, you would be able to move it into a private cloud and run it yourself if you had that economy of scale.
Great. Time for one more. This one over there.
Thank you. Hi, great presentation. Really like the product. But questions. NoSQL databases have a very attractive feature that you can do schema on write. That is, you don't have to commit to a given layout of the database up front. I get this sense that you're doing away with that, right? You're moving back to, no? It wasn't clear in your presentation.
Yeah, I'm sorry about that. We actually, this is in flux. We are just starting on the structured. It's moving actually pretty quickly, and we're having some internal debate. But we're quite sure that whatever we do, especially with just adding to the schema, is going to be like trivially fast and easy. We're not quite sure whether it's going to be just implicit or not. That's certainly an option. One thing that we were considering is that schemas are always there, but you can enter the database as though it's just a simple document store. So if you want to just throw a JSON blob into it, or like if you're using Go, just like throw a struct directly into it, it basically deconstructs that and will create a schema that's implicit. If there's a number in a certain field, right, and then you try to throw a string, it will warn you about that or complain and have an error. You can always inspect that schema, and you can even start with it and make it explicit if that's what you want. But we're certainly going to, whatever happens, like the real benefit, and I agree with you, for that NoSQL offers of having such flexibility with additive pieces to your schema is something that we're going to maintain.
Great. On that note, thank you very much. You'll be around after this, right?